right. So, yeah. So obviously most of you took the midterm. With regards to that, you'll get your midterms back on Tuesday in lab. With regards to the grades, the average was around a 71. The break point was basically we had a bunch of I think one person got a 73, and then everything was either at least 5 points above that or at least 5 points below that. So it was a fairly large dispersal in grades. We also only had 4 A's, which I would assume, normally I would expect more. The average grade, again, was a 71, which is fairly normal for this class. With regards to any... But, we went through and we were grading it yesterday. So things that I noticed, first off, most of you did score at least 16 points on the essay, on the given essay question. Not essay, but, if you didn't write much on that one, you had to be very accurate with what you did write. So the drawing actually was surprisingly brutal. That was actually the brutal section, not the one that I said, here's a bunch of code, draw what that did. A lot of you did get that one. It was actually the ones after that I assumed would be freebies, of the draw what happens with when you add or remove things. That was surprisingly brutal on it. It's possible that we graded that too harshly. So Kenichi specifically graded that part. We each took a bunch of pages and graded that. So depending on that, there were only, now with regards to what I saw, there were only a few of you that graded, only 1 or 2 of you stood out as having coding things that were extremely problematic. Other ones of you made a decent stab at it, but just didn't get a good score. It varies from person to person. As far as any kind of makeup or recovery on it, I haven't decided yet as to what that will be. Still have some students that need to take that. But again, I'll hand it back on Tuesday. I plan on and then on Wednesday, you'll be able to look it over on Tuesday, and then be able to come to class on Wednesday with any argument that you have as far as were you graded too harshly? Because our philosophy there is that if we're in doubt as to whether to grade should we give you more points or less points for partial credit, we err on the side of giving you less points, because I can always add the points back if we misinterpreted it or misread something, because handwriting and issues like that. Whereas I can't take points away if you show that you actually didn't understand what was doing. Now, with regards to the what people wrote on the back of their exams, a lot of you enjoy the way the course is going. For those of you who had suggestions on what to change, you said more in-class instruction time. In other words, less time with, less of me going around and more and me going over examples and stuff like that. And I think for these next few assignments, that's definitely something I can do. So that's where I plan on doing that. But before I do that, any questions about the exam or anything like that? So when is do I have May's currently set to be due? End of the week?
Tomorrow.
Tuesday. Okay. And how feasible do people think that is? No?
Can we have the full day Wednesday to demo for you in class?
I mean, I can provide more time for that. Let me go ahead and see what we have. Okay? So let me go ahead and see what we have. So not grades, we don't want to do that. That'd be silly. So assignments. Normally I find we have plenty of time to in this class to kind of make time. February 27th. That's okay. For some reason I thought that would be more time. I'll be adjusting the due dates over the break. With regards to this, I can give you a few more days on this one. Let's go and go through the end of February, shall we? So, okay. Now, with regards to that, let's also make sure you get on the right path with this. I plan on grading on showing you how to do some of this. Next, other questions about the exam or any suggestions as to, again, you haven't seen your exam. I've got a blank sheet with me if you want to reference it and ask me questions about your particular answer. I do remember a lot of what happened on the exam for some of you. We do try to grade it anonymously so that we do not know who. So we can't. So basically, we flip over the pages and we grade it. We do all of everybody's page 2, and then all of everybody's page 3, and then everybody's is page 4. So we don't know whose it is. For most of you, some of you have rather distinctive handwriting, and so it's hard to separate that out. But again, a lot of times we just simply grade harshly, and I'm like, if you can elaborate on that, great. I've given points back. Also, the other thing is, remember that we're human, and we can easily miss typing in something into the calculator when we're totaling up your score. There has the highest point on differential between a grade put in and a grade. I think I've made a 15-point error against the student before in terms of addition. So be sure to add your points up yourself. Because that kind of mistake does happen, be it an input error or a calculation error. All right. Any other questions? So what we're going to look at is the maze. So over here, right, with the maze class itself, hopefully you've been looking at it since it was originally due tomorrow. You run this, and it generates a maze of a certain size, which it will do while we're looking at it. Now, the main way this works to move through the maze is that you push things. Now, I've got this for loop over here for a reason, because what we're going to do is that we are going to, I'll make it run 8 times so it doesn't risk going out of bounds. What we're going to do is I'm going to kind of show you how to operate going through this maze, okay? Which is that you push cells onto this. So what we can do here is we basically would say so we've got this. Now again, what you want to do is when you're done with this, you'll want to replace this with a while loop. To move through the maze, we just push our current square onto the stack. Push cell, and then we would say, let's see, stack dot peak to get where we currently are. So cell current is equal to stack.peak to know where we are. Okay, because while we start at this location, that really doesn't help us too much. Okay, let's say we want to move south. We would say maze. So the maze is our 2D array of cells. Current dot row and current dot column, and this would push where we currently are onto the stack, because that's where we currently are, the current row and current column. If we want to go south, we subtract one from row to go north, so we would add one to go south. Okay? Now if we run this, this actually wouldn't really help us too much, because while we're putting things into the stack, we aren't necessarily marking that we've been there. Makes everybody following me so far? So to mark that we are in a current location, what we'll do is that we'll take a look at the stack, and then let's see, what did the PDF I have say as terms of the order of operations here? Did I want you to mark the current location as visited? Okay. Mark the current location as visited. So to mark our current location as visited, we just choose a color other than green, or sorry, other than red or white. To change the color of a cell, we'd say set background. Right, you can see that over here. It's the set background and set background. And then you can either create a new color, right? You can make your own custom color. but honestly, most of you will, like me, are gonna probably want to be lazy and just use a built-in color. And it accepts both shouty case and lowercase. So let's go with magenta to say that's how I move. That's a nice bright color. Stacked up push. Okay, and then we'll keep moving. And so we'll set the first, so basically this is, so we set the current location and then we move, we set the current location, then we move, we set the current location, and now we're currently here, right? That's fine, that we didn't color where we currently are. That's a fence posting problem, kind of, for you to figure out on your own. But you see what we did. That's how we move down, okay? Now, part of the issue you might run into is that if you keep wanting to move down, but you can't necessarily. Because if we run this now, we'll get an error where it's going to say, hey, you tried to, this is out of bounds. Array out of bounds exception. Why? Because we went all the way down, because I'm working in a 10 by 10 maze, and I told it to go down 15 times. So as soon as it got to as soon as it got to row 9, it tried to go to row 10. Row 10 is out of bounds, right? Everybody following? Row 10's out of bounds. Can't go down through row 10. So that's an issue. So part of what we should do is use an if statement to protect ourselves from going out of bounds. So the first part of our if statements, of all these if statements, I don't know why I write 4, but it's an if statement. The first part of writing these if statements is basically if current dot, and then so current, our cell, is an object that I've made, and you can check it out, right? It's the third class I gave you. It has, besides row and column, which is extremely useful to have, it's got these walls. So if current dot south wall, if not a south wall, okay, if not a south wall, then move. If there's not a south wall, we'll mark our location and then we'll go. Okay? And you can see here that we don't move on from this point. We just kind of stop. Now, one of the things I did for you for convenience sake is that the boundaries, that invisible boundary around the maze is actually surrounded by walls. So if you're on this top row and you ask if there's a north wall, it'll say yes. That way you don't have to check for for going out of bounds. That way you don't have to worry about if I'm on the first row or not. You can just write code that works. You just check if there's a wall. Now, you could of course write code that ignores walls, but that won't be a good solution. Like, for instance, I'll take this and just simply do this. So I'm just copying this and so let's see, east. I always have to remember, wait, am I going north, south, east, west? What are this directions names again? Rather silly, I know. But let's go ahead and do column +1 to go to this way, right? Now, normally you don't want 2 loops in this code. I'm just doing this as kind of an example to show you that, let me see, if there's, actually, so that one I said, if there's not an east wall, let's just go ahead and set it to 5 and remove that if statement for a second. Right, so now if I don't care if there's walls, I'll just go, I'll Kool-Aid man right through those walls, essentially. Right, see, it's hard to see over here, but there's a wall right here that I just kind of stepped through. So that's why you want to check for the walls, because that's how you know whether or not you can, because not only does it keep you going from out of bounds, it keeps you from going through these walls. Now, the maze that I create, it's going to lead to a very kind of jagged path, like that, or maybe like that. It's going to always be like a diagonal path with very little backtracking. In fact, the way it should look, if you do it, you'll have a path, and then you'll have a white space above here, and then you'll have a gray space over here, or whatever color you're going to use for visiting. So that's how you move through the maze. Now, so believe it or not, after that, this is actually going to be fairly straightforward. It's the easiest thing. The easiest way to make it more difficult is to just overcomplicate it. If we go back to our document, our maze solving algorithms has this already set up, and we have while this is not done and the stack is empty. We're not gonna that for loop. We're gonna keep that for loop in place here right now for that, right? Because the while loop that will be our last step, completing the while loop. For right now, we'll just use a for loop so we can do this multiple times. It says to peek to get our current location. Great. Then if we can go north and we haven't visited there yet, okay? So what is if we can go north? How could we tell if we can go north? What tells us whether or not we can go north? Yes?
If there's no north wall.
Right, if there's no north wall. So if current dot if not current north wall. And this is the last part I'm doing because I want to teach you a little bit about why we have two of these things here. Okay? And we haven't visited there yet. Now I've got this function called visited, which takes in a row and column. So if you want to go to the north, and visited. Let's see. So and visited, it takes in two arguments, a row and column. So if I want to know if I visited the north location, what do I put in? Yep. Row current dot row current dot column. Yeesh, I'm just typing all over the place today. Current dot column, not row, column. All right, always look at what you're typing. Row, column over here. And that's actually probably most of the code I just gave you over here. That's okay. It's been we're all getting ready for the break. Okay, so if there is not a north wall, and I haven't visited it yet, in that case, I'll try going there. So we'll go ahead and grab this. Set our current color there, and rather than going down, we'll say we'll try to go up. Okay? So this is just simply checking to go up. Now in the maze I generate, you never actually have to go up, but if you want to do the extra credit with the def for search maze, you'll need to check about going up. Okay? So if we run this, it's gonna check and it says, oh, I can't go north. And now since we're going and then it says if we can go down, we do go down. It doesn't bother, we haven't bothered adding the check to see if we've gone down or not. But notice that we keep going down, even though there's no north wall over here. That's because the second check says, oh, is a location above me visited? How do I know if it's visited? If it's a different color than white or red. Okay. Now, the main thing I want to bring up here about kind of Java and C languages in general is at our starting location, right? You'd think, if you look at it, you think to yourself, we should actually be getting an out of bounds exception, right? If not current north wall, if there's not a north wall, and, right, so that's false, and visited row -1, column -1. So this is a function call which would pass in -1, and then we would do a lookup operation over here on -1, which in Java should fail. But we never get an array out of bounds exception. Why? Yes?
Isn't it because the way you generate the maze, everything is a wall, and you need walls as you move?
Yep, I mean, but there is a wall. This is false, right? I'm asking about it. So this is false, right? So what happens because this is false? do we ever actually call this? No. What's that called? Anybody remember? Where basically, where we have an and statement, and if one side of it is false, we don't bother looking at the other side. Everybody remember, do people know that happens? Right? It's a feature in these languages called short circuiting, where basically Java and C languages do this too, where, oh, here we have no north wall, so this is false. And because it's false, I'm not going to bother checking the rest of the and statement, because if one part of the and statement is false, the entire thing is false. So I'm going to save computational power and not keep going on. So that's why I don't have to worry about it. It's actually a very useful thing for when if you can make your and statements like this, because otherwise we'd have to write another and statement and say, and if it didn't work like this, we would have to say, we'd have to have this as a separate if statement and have an and statement over here saying, and it's not -1, and we're not on row 0. But what happens is that we short circuit. And that's why we actually have 2 of these. If you just put in 1 in Java, this should crash if I remember everything correctly. Yes, it crashes on visited. Because in this case, index -1, right? Because in this case, what happened? When you have one and, you don't short circuit. You run both sides of it, regardless of whether or not you could. So that's why we've always been putting in 2, in case you're wondering, because short circuit is just much more convenient for our logic. Yes?
Shouldn't it be not visited?
Oh, and not visited, yes. Not visited. I must have accidentally erased that while I was typing it. I think I said not visited while I was writing it and just forgot to. One of the dangers there. There we go. Not visited. So you want to add you want to do something similar for this for north, south, east, and west, right? Where if there's no wall and you've not visited that, you set your current background color to that, right? So you have this one for north, south, one for east and west, and at the end we have an else statement over here, which I'll leave you to fill out on your own. So if you go to all 4 of those directions, okay, this is not helpful, so what do I need to do? I need to hit zoom in over here. Okay. So otherwise, if you can't go north, south, east, or west, you're at a dead end. And if you're at a dead end, that's where we backtrack. So this is just a remark here. So that's not actual code. That's just us realizing we're at a dead end. What code do we need to put in? Mark the current as a dead end. To do that, what I would do in that case is I'd use a separate color. I typically use gray to mark that this is to visually distinguish between our path that are a good path and a path we've already been down. Okay? I mean, you don't have to. You just otherwise visually wouldn't be able to tell what's the path and what's the bad path. So we'll mark it gray if we're at a dead end, and then we pop the stack, right? And if we pop the stack, we go back to our prior location at the top of this, because now we'd have something new to peek at, which would be the location we got from there, right? So again, what we have for our maze is that we have two tools. We have our thread represented by the stack, and we have a bunch of chalk to mark our location, or paint, or or maybe it's just making scores on the wall. But whatever it is, that's in the equivalent we have in Java is to change the background. Okay, then once you've done this, I would gradually increase this. Of course, once you get to the end, you'll kind of get into a weird kind of location. But once you find, oh yeah, this will make it all the way to the end, that's where you want to work on your while statement. And it doesn't have to match exactly. If you find, oh, I've made it to the end, so break, that's an acceptable solution as well, right? As long as how do you know when you're done? If you have a visually identifiable path from the top left corner to the bottom right corner, the path you've already searched is visually distinguished, is visually different, then I'm happy. Make sense? Again, so I'd program in the code. This one is actually, again, fairly straightforward. Okay? So this used to be 50 points, extra credit was 5. This used to be a half credit assignment. Since it is a full credit assignment, it is, I'll say that the extra credit is worth 10 because it is a pain to do to do that. Maze generation algorithms. Now, that being said, if you want to try your hand at a different maze generation algorithm other than randomized depth first search, you can. Randomized depth first search kind of looks like this, where basically what we're doing is that this maze is going through, and then when it corners, it's randomly choosing somewhere to go. When it corners itself, it backs off. Okay, and then so that blue is basically where it said, I've already dug out and I'm not going to try to go in that direction again. Right? Whereas, so now everybody kind of see how it's doing that. It's just it's just randomly filling all the spaces and deciding whether or not to remove a wall or not. Okay. So this is just randomized depth first search. Now, each maze generation algorithm has its bias towards maze. Depth first search loves because of the way it's randomly generating these spots. It just loves generating these long, windy corridors. Okay, it's just the way that it happens. There's the algorithm over here is, and again, it's you'll have to like think very differently over here. In fact, you may have to change the code I gave you. You'll want the iterative implementation with a stack. So mark it as visited, push it onto the stack. You may want a secondary array, one that says whether or not you visited these squares rather than coloring them. Or maybe you would do color them and then you just color everything white at the end. Okay? And then while the stack is not empty, you have to basically choose this one's the tricky one. How do you choose one of your neighbors at random? Right? That's what kind of becomes difficult. Again, you can, but the algorithm works also with making hexagonal mazes. There's other kind of ways you can do this with prims and kruskals, which are things you'll learn in graph theory later. Basically, connecting 2 points up, just choosing any 2 points and connecting them up, and then proceeding to connect more and more points. One of my personal favorites is this recursive division method, where basically you split each space into quarters, and then you proceed to split. Then you open up. You create a opening with 3 of those, and you just simply do that to each space recursively. There's a lot of different ways to do maze generation algorithms. In fact, this external link over here about is actually a pretty cool slideshow about how mazes make very good practice on algorithm skills. Exactly, blah, 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 high level kind of things. But it's got some wonderful examples on graph theory, talks a bit about graph theory, and he's got these embedded examples as to maze generation algorithms and how they work, introduction to other algorithms. It's similar to what I did, only much more complicated. And then recursive backtracker again is what we do over here. The nice thing about other things you can do is you can make these kind of, woven mazes with some of these algorithms, which is pretty cool. All right. Now, any questions about this program? Now that I've kind of shown you a lot of the way of how to do it. Hopefully, this made it a whole lot less scary. Okay. So I believe I said I'd start on this side of the room today. So.